Ah,
That lady must get very bored saying that all the time. Well, good afternoon. My name is Chris Rees. I'm the chairman of the CCS, and it's my pleasure to introduce Barry Landy this afternoon. Barry has a degree in maths from Cambridge and started doing high energy physics. And then after a couple of years, he realized that computing was more fun. And he asked Professor Maurice Wilkes if he could join the mathematical laboratory, which he did in 1963, writing the operating system for Titan, the Cambridge Atlas II, and realized that he'd found his niche. And I don't think he's left it ever since. So Barry's computing journey has covered Atlas, IBM MVT and MVS, familiar to me, and many small computers. And his most recent employment was as an expert in a lawsuit concerning IBM copyright. We must swap notes on that afterwards. Barry, over to you.
thank you very much. I need these to read my notes. Let me first of all say good afternoon. What a pleasure it is to see people here. And I know there are quite a lot of people also connected via Zoom. I particularly want to mention David Hartley, who was an eminent member of this society and also in my department. So David, welcome. Nice to hear. Nice that you're there. A general comment. What I'm going to talk about is 60 years old. It happened 60 plus years ago, and memories are fallible, and I tried very hard to research the facts. I found it difficult to find some things out, and I found it difficult to find people who knew. So the facts I failed to find out, please forgive me for not finding them, and if I got any wrong, please forgive that as well. So just a comment about the early days. So for me, the early days of 1959 to 1963, everything was very different. The technical world was very different. There were no computers, few computers. Phones meant something attached to a wall. Calling somebody when away from home meant using a phone box. In that world, computers did not participate in any future planning I was making. Although when at school I did go to a Royal Society lecture on transistors, which were things about that big in those days. After graduating at Cambridge in 59, I should say 1959 in case somebody's got the wrong century, I moved into the theoretical high energy physics department, and I also moved out of college accommodation into a flat. In my first year, I had a very interesting topic, which required calculation. And the way to do that, I was told, but for sure, the way to do that was to use an electric, not electronic, notice, electric calculator. Some of them were not electric, some of them were actually manual, but this is a calculator. I don't now remember which it is. I got that picture off the internet. My experience of that was sufficiently negative that I made a vow never to do it again. It was a week's work to solve some equations. At the end of that week, I had no knowledge of whether what I had done was right. The only way to verify it being right was to do the whole thing again. Then you get two different answers for sure. So you have to do it again. You know, that's definitely not what I was going to do. So my flatmate had earlier that year, 1960, taken a course in EDSAC2 programming. He was very enthusiastic about it. So I thought that was the way to go. For those that don't know, EDSAC2 was the replacement, obviously, of EDSAC. It was about 60 times faster. Instead of the famous mercury tubes, it had magnetic core memory. Imagine that. But the cores were macro. You could see them. It was also the first microprogram machine, although Dick tells me that's now debated. So I moved on to EDSAC 2. That's EDSAC 2. Or rather, that's the room in which EDSAC 2 lives. If you see the doors at the back of the room with glass windows, behind those are these horrible calculating machines. And I spent my week. The EDSAC itself is hidden by the boxes to the left of that picture. And the rest, it's a job queue, isn't it? It's people queuing up to have a job. And the lady on the left of the computer is the operator. Val, for anybody who knew her. And that's an EDSAC 2 replaceable unit. It's one I happen to have in my room in college. So at the end of that period, I spent 2 years still doing high-energy physics, but I was also using EDSAC. I must have spent as much time with EDSAC, talking to EDSAC in the math lab as I did to the people in my group. I became very enthusiastic, as my wife would tell you. Apart from writing programs for my research, I also wrote programs for EDSAC. I debugged a library routine. I wrote a library routine to use magnetic tape, you know, the things that people do when they're putting their toe in the water of becoming a software programmer. I also joined a challenge to write programs to solve what was the departmental Christmas challenge. I was, of course, a research student. Research students are the lowest of the low. We didn't have any undergraduates on the computer then. They would have been the lowest of the low, but I was the lowest of the low. So in order to get the time I needed, I had to do my programming at night. So A, I got home late at night, early in the morning, and B, I had to become adept at fixing things, because these computers were not like today's nice little devices which run forever, I hope. But they broke down a lot, and I had to run the engineer's test suite. And as a result of what that told me, I might change one of those replaceable units. Or indeed, if I was very brave, a valve. At that point, I realized that I was much more interested in the computing, much more than the physics. I went to David Hartley, in fact, and asked him for his advice. And he said, go and talk to Wilkes. So I went to talk to Wilkes. That's Wilkes, for those who didn't know him. And I asked him if I could have a job. And he said, and I'm quoting, just the sort of person we are looking for. Come back in September. That was it. That was my job interview. And the only one I ever had until 2023. But 2023 is a different story. So at that point, I started in the mathematical laboratory. And my work there was to program Titan. This is a photograph of Titan. It's a staged photo because the room is incredibly tidy, and the doors are on the machine. Can I point at this thing? No, okay. Well, you see the boxes in the back. Does the mouse show? No. Does the mouse show on the screen? Okay, the big boxes are Titan. Big boxes are Titan hardware, and there's 2 tape drives there, and there's a power supply there, and there's 2 engineers you can see. Hidden by the stanchion of the gallery is the engineer's console, which the engineer is obviously doing something with. And at the bottom right of the table where the other engineer is, you'll see a typewriter. That plays an important part in the story. So Titan was a cut-down version of Atlas. Why was there a cut-down version of Atlas? It's money. Follow the money, always follow the money. The reason why we got an Atlas 2 instead of an Atlas was because the government wouldn't pay for an Atlas. Simple as that. So what that meant was that we didn't have the hardware in Atlas which did all the memory management. And that's a very important part of the operating system, obviously. And that meant that Atlas II could not run the same operating system as Atlas I. So we had to start from scratch, although we copied a lot of the design principles from Atlas I because they'd done it already and that was sensible. That project was led by David Barron, and the people working on that were Roger Needham and David Hartley. When I arrived, the machine was still being commissioned, and this is sort of a photograph of the commissioning. And that's a replaceable unit for Titan. And I do have, by the way, some things to look at on the desk here. Not now, but after the talk's over, people can come and have a look. So at that stage, people were running test programs. Some of the supervisor was already written. I don't know what they did before I got there because I never asked. I believe that the engineers were written in machine code and not assembler, and they could only see the results on that engineer's console in the lights, because I don't see what else they could have done. We used an assembler. I don't know the origin of the assembler, and there's nobody left to ask. It was called IIT, and I believe it was implemented by David Wheeler, that most people will have heard of. If that's correct, I suggest that IIT might stand for Initial Instructions Titan, because he did that on the EDSAC as well. That's my first assignment. My first assignment was to write something called TSDS, Titan Supervisor Diagnostic System. The first sentence says TSDS enables the operator's typewriter to be used for online control and error diagnosis of software programs in general and supervisor routines in particular. And the plan was that that golf ball typewriter could be used as a debugging tool instead of the engineer's panel, so that you might run a program, it dies or comes to a stop, or the engineer's lights show something. You can then read in TSDS and examine what was installed to see what had been happening, look at the registers and so on. And you could also then run the program under control of TSDS to see what it was going to do, even if necessary, single step it. But my first job was to get to grips with that typewriter. Why was that a job? We had been given that typewriter and we knew the interrupt it would use, but we didn't know its code. So I had to write a program to discover the code for a device whose code I didn't know. It's an interesting problem. Think about it. For TSDS itself, David Barron had given me a very simple specification, which was too simple. And I found out quite quickly, it's harder to follow a simple specification than a general one. So without telling him actually, so I swapped to a general specification for input routines, which was much quicker to program. And I think after that, they didn't bother giving me instructions. It's worth remembering that in 1963, the normal way of using computers anywhere, as I'm aware of, was to run one job at a time. Program and data read in from cards mainly, although we use paper tape. Atlas also used paper tape, I think. And there was no multiprocessing apart from interrupt control. Atlas had multiprocessing. We had multiprocessing as a design principle, presumably inherited from Atlas. Okay, Titan, this was the specification of our Atlas. The processor was 5 microsecond instruction fetch and 5 microsecond memory. 2 microsecond memory was available, but that's another financial question. The government would not give us the money to have a quick memory. Words were 48 bits, same as Atlas. They could be split into 2 half words of 24 bits, or 8 6-bit bytes. The character set was in 6 bits. Instructions took all 48 bits. As well as all that, there were 127 so-called B lines. I don't know why they were called that. They were 24 bits long in the fast memory, and they were split up in the way I've got down here. B0 was always 0. B1 to B89 user programs, generous. B90 to 99 were supervisor routines called by the user program. B100 to 119, the system used that, either for supervisor routines or for interrupt routines. And while it was just a single processor machine, because I don't think there were any multi-processor machines in those days, there were 3 different program counters. 125 for interrupts, 126 for supervisor, 127 for user program. Hardware was floating point. Sorry, floating point was hardware. And there were 6 tape drives, but we did not have any disk or drums. We had memory protection, which is very different from Atlas. 4 registers in hardware defined the memory that you, as a programmer, were assigned to. Your program started at the register 1, it finished at register 2. If you tried to access anything outside that boundary, you would get a fault. If you wanted to do a transfer to tape, then there was another pair of registers, strangely R4 and R3 in that order, which was the lower limit and the upper limit of a region which is locked for a transfer. Because if you are transferring to tape or disk, you cannot write to it, or you may not. It would be a bad idea to write to it while that was happening. So when I joined the team, the basics had been designed: control of interrupts, the mechanism of the supervisor operation. And in 1964, I may have that date wrong, we were joined by a team from ICT who had brought over Ferranti, who made the atlases. And jointly, we were writing and commissioning the new operating system, because they had 2 more atlases they wanted to sell, and they thought that what we were writing was going to be a good way of selling these machines. Titan was already in use for users with a temporary operating system. So all the development had to take place at night, evening and night. And since I was in charge of the debugging effort, I was helping people run their jobs, and I was helping them debug their programs, for which I found out I had a major talent. So it's one of those things. I'm sure a lot of people in the room have talent for debugging things, but some people can and some people can't. And so A, because I was the youngster, B, because I could do the debugging, that was my job, and I had to do it at night. So another reason for coming home late, or early, whichever way you like to put it. That joint venture ended in 1965. The first critical thing that happened in 1965 was that Aldermaston bought the second Atlas II. Being what they were paranoid about programming, and not unreasonably. And they said they could not permit multi-programming. They could not have more than one user program running at a time. You're shaking your head, Dick. I can see why. Yeah. Anyway, so that scuppered the joint effort, because if they're writing an operating system for Aldermaston, there's no point in helping us write our operating system because it's different. The other thing that happened in 1965 was that Wilkes went to America. Not for the first time, I might add. And while in America, he went to Cambridge, Mass, and went to MIT. And at MIT, he had demonstrated to him CTSS, their time sharing system. I'm sure that it stands for Cambridge Time Sharing System, but not our Cambridge, their Cambridge. So he saw that when he came back, believe it or not, he was able to demonstrate it to us using a 10 character per second teleprinter on the telex line. I don't believe it now, but it worked. It was very slow, but seeing what happened was the important thing. And he insisted, and he was right, that the supervisor should be modified, even though we were halfway through writing it, to permit online interaction with terminals. Since we'd insisted on maintaining multi-processing, we were fortunate that we had the right basics. If we had stuck with a one program at a time system, it would have been very difficult. David Barron had left us at that point to go to a professorship at Southampton, and so Roger Needham was in charge of the project. Okay, so we are sitting there with what the hardware we've got, and we want to produce a system for time sharing. What didn't we have? A lot of stuff. We didn't have anything to do two-way communication with a computer. Obviously, without that, you're lost. You have to have that. We didn't have a data store for users. All we have is mag tapes. Mag tapes are fine. They store data, but they're cumbersome. And to get the data to an online user would just be really, really bad. Wouldn't work. And of course, that's the first two items on that list. The second pair of items are software. We need control software to deal with a large number of tasks and a large number of users. It's a different game. So, oh yes, we also made a decision against Wilkes' wishes that our system had to run 24/7 with odd breaks for software time and stuff, but in principle, it was available 7 days a week, 24 hours a day. And I think one of the reasons why Wilkes was against that was that when he visited MIT, CTSS was only running 3 p.m. to 5 p.m. at a time when no jobs were running. That's not how it ran eventually, but that's what he saw. So he thought it was necessary. I also made the decision sometime, possibly then, possibly later, that the same command system should be available in jobs as well as online. But possibly I only made that decision when I implemented it. But you know, these things do happen that way. So input output. The only candidate was that thing. Teletype 33, which ran at 10 characters per second, which was fine as far as we were concerned. It didn't seem slow at all. Well, I know we all laugh now, but
I'm laughing because I'm agreeing with you. There.
agreement is good. That was Leeds, yeah?
Yeah.
I couldn't see who was speaking.
David.
It was David, right. So it's got the basics. It's got a typewriter keyboard. It's got a piece of paper onto which the results are typed. And if the machine talks to you, it's typed on the paper. Because it was a telex machine as well, that's why it's got a paper tape reader. So we had to get some of those. They were easy. That's easy. They were easily purchasable. But we had to connect them to the machine, to the hardware. So we had to design and implement a multiplexer to which these machines were connected, and the input, the data traffic from there into the atlas. The multiplex had 64 lines, and I believe a maximum of 26 could communicate with the computer simultaneously. At a later stage, we took 3 of those lines and multiplexed them again into 12, increasing the number of lines we had available to 73. And I have a feeling that that was also dial-up. I know we had dial-up, and I don't know how we did it. In 1967, we went to a thing called Data Fair, which was a computer meeting. I wouldn't call it a conference because it wasn't a conference, but people displayed their wares. And we went there to give a demo of our time train system, which was in full operation at that point. We were the experts on these things with computers because nobody else used them that I know of. And this was a remote connection. Southampton is not Cambridge. And we had to have, by the rules of the post office, we had to have one of their engineers there. He knew nothing. We had to tell him what to do. And he explained to us that the post office rules were that management went on courses first and the engineers last. Might still be true. These things worked by producing a character which they sent down a line as 10 bits. And those 10 bits were then assembled to make a 6-bit character. And that assembly was done in the multiplexer. And then when that was ready, it sent an interrupt to the machine. So one character at a time, one interrupt per character. Okay, data storage. That was another main problem. The other main problem we had to solve. I lost it. That one. The other main problem we had to solve was the file store, a place to put data which wasn't magnetic tape. We got a present. Again, there was a money problem. We didn't have any money. So Basil de Ferranti, presumably by then ex of Ferranti, gave Wilkes, I think he was very friendly with Wilkes, a data product disk store, which was enormous, about that sort of size. I've not been able to find good information about how big it actually was. It had, I think, 12 platters. Somebody might know, Dick might know. And they were 24 inches in diameter, big. Each platter except the top one had one single reading head. So if you had to read something there and something there, the head had to travel. So that was slower. The top platter had fixed heads for each of its tracks. So that was quick. We eventually had two of those devices. I don't know where the second came from. The capacity was 8 million words per unit. Doesn't seem huge now, but it was enormous to us. And of course, we had to do a great deal of programming. The software design of the file store, the same as magnetic tapes, was that we pre-blocked the store. The tapes were pre-blocked into blocks of 512 words. The disk store was pre-blocked into blocks of 512 words. And we then maintained a map of those blocks. So a file did not have to be consecutive. It could scatter up anywhere on the disk. And we maintained the chains to tell us where things were. And they were chained on the map, not on the disk. So this is the team. Roger Needham in charge. Roger, with David Hartley, myself and Mike Guy were the main in-house team, if you like. We had 2 research students, Peter Radford and John Viner. We had to find projects for them which were slightly separated so they could write a thesis and not just be part of the general work. A man called Sandy Fraser joined us in 1966, I think. These are the people who did the first bits. David Hartley wrote a login process, very simple. I did the file store programming and job scheduling. David Barton, who was a user, did the first command processor. Sandy Fraser did the file store interface, and I'll come back to that. Somebody did a line editor, I don't know who. And Steve Bourne, you might know the name, Steve Bourne, who was a user of our system then, wrote a context editor. And that stuff was enough to give us a proof of concept that the thing was going to work. We also had to run jobs, but we didn't have a well on tape like Atlas did because we had a disk. So we did the well on the disk, which was much more efficient. We had to design all these processes, which I just mentioned. And early 66, I think, but it might have been mid 66, the proof of concept system was working, and we were all using it. Nothing else would do. You can't do a system for other people. It has to be for yourself, otherwise it won't work right. And the full system was open to everybody, well, a few hundred perhaps, on March the 22nd, 1967, a date my wife will remember. We immediately noticed that we stopped using secretaries. If you can type your own documents and print them out, why do you use a secretary? Okay, so the system was still very limited. We had this amount of stuff. We had 64K words in memory, which later was expanded to 128, which made a huge difference, and that's as big as it could get. Supervisor was 15K fixed, so 15K of that 64K was immediately taken away from the user, and 25K of supervisor, so 40K supervisor in total, but 25K was paged in when it was necessary. So of the about 40K available to users, and the job sizes were allowed to be between 4K and 32K. So we didn't have paging hardware. So the only way to deal with the fact that we've got so many jobs with such a large demand of store, and we've only got 40K of store, is to swap. We could have more than one job running at a time, more than one user in store at a time, because after all, if the user is only taking a small amount of space, we've got 40K, but we certainly couldn't run two 32K jobs at the same time. Check I've got the right slide. So we had to swap. We didn't have paging hardware, no one-level store, lots of users. We have to swap. Swapping means taking the stuff from the memory, putting it onto disk, making sure you know where it is so you can get it back later when you give that user another turn. Swapping is very expensive in cycles and I/O capacity. We had to reduce the amount of swapping. So we invented something. We invented something we called normal mode. What else would you call it? Normal mode is what we wanted most users to do. In normal mode, there were some common applications which were made system resident, like the command processor, the editor, one or two other things as well. They had to be very carefully written to be location independent. Right? We didn't give them a region starting at logical naught. They knew where they were in fixed store, so we could have lots of them. So they had to run without relying upon where in store they were. And they had to be re-entrant so that multiple users could use them at the same time. And we told people when they wrote these things, they had to be very frugal with their workspace. The smaller the workspace, the less swapping. So if you could do your job in 64 words, that'd be wonderful. Everything else, everything which wasn't in one of these common programs, was done non-interactively. Doesn't mean that you had to send a job and wait for it forever, but it didn't look like that. But what you did was to prepare a program, the list of commands, which bits of this you're going to read, and you would run that online. But you didn't have interaction with it. So you didn't have to hold up waiting for you to type at the terminal. It would run, then when it finished running, it would type the output to the terminal. So it was almost interactive. You'd prepared a job You gave it to the system and it came straight back to you maybe a minute or two later. Almost interactive, almost as good. I wouldn't pretend it's the same, but that reduced our swapping a great deal. And of course, a user could run the job. And it used the same command language. All he actually had to do was do the same work he would have done to run that job as a non-interactive piece of code in his session. All he had to do is type the command run job and give the name of the file, and it would run it as a job. He didn't have to learn our equivalent of JCL, which nobody else does. IBM still don't do that. So there were several other ways you can run. Naturally, there was something called expensive mode, where you had full interaction with anything you wanted to run. You had to have privilege for that. Not many people were allowed to do that. Obviously, we were. Not for the reasons you're thinking, but because we might need to debug things. And but we were honest and ethical, and we didn't use expensive mode unless we had to. And there was a more restrictive mode called edit mode, where you could do typing and editing and printing, which is what most of us do most of the time, actually. And it was cheaper, that is, for the system, and cheaper for the user who had a quota of time he could use, and so he was charged less for an edit mode. Swapping is still a problem, and we had to sort something out. And we went to David Wheeler again. David, we have a problem. David was wonderful at solving computer problems, going back as far as EDSAC, the EDSAC, and EDSAC 2. And we said to David, we've got this problem, what can we do? And he invented something. An extra memory region addressed by a thing called register 5, R5, registers 1 to 4, I mentioned it earlier. This R5 was an 18-bit address, that's the full address in memory, of a small region. 3 bits said how big it was, whether it was 64 words, small, 512 words, or 4096 words. And it was addressed in Octal in a different way to other bits of memory. So if you're interested, that's how you address different sorts of memory. So the way that these wonderful programs, which had very small memory, worked was that they had the data in a small block, ideally for 64 words, but maybe 512, pointed at by the register 5. The program itself was one of these system resident programs, didn't need swapping. All that needed swapping was this small region. And that went to the fixed head platter, so it was done quickly. So that made a huge difference to the overheads that the system had. Without that, it just wouldn't work, especially when we moved to having lots more users. Even so, with a full batch load and a lot of users, swapping took a lot of cycles. Among other things, we had to save all those B lines. Users, B1 to B99, had to be saved. And the way I did my program, the way I did it to start with was simply having a loop, a 2-instruction loop. I won't go through the details of how that can be done, but it can be done on Atlas. And you just run around this loop 99 times, and you store each of the registers. That is slow for reasons that Dick will remember, because the atlases had memory lookup for instructions about 5 deep. So if you're running a program that says go straight through memory, the next 4 instructions will be waiting for you. And if you do a jump, that breaks down. It doesn't know where you're going to jump to. So the 2-instruction loop was actually slow. Apart from obeying twice as many instructions, as method B, which was writing down 99 instructions to store each register one at a time. And it was much faster. We also had interleaved memory, so I didn't actually write it store 1, store 2, store 3, store 1, yeah, 5, and yeah. And that gained 5% of the CPU. It's a lot. Something else which has nothing to do with the main topic, really. I wanted to mention this because it's an interesting piece of computer history. I don't know who invented the tunnel diode, and I don't know who invented the tunnel diode slave store. Apologies for the name, but that's what it was called. This was a 32-word store, very fast. It slaved a word from main memory into one of those 32 words. So it took the last 5 bits of memory to address the slave store. So the slave store was always full of instructions that had been used. Each word, of course, had another 13 bits to say which actual word in memory it was. If you wrote a loop which was less than 32 words long, by the time you've gone through the loop once, it will all be in slave store, and it will then run very fast. Lovely idea, but tunnel diodes were not reliable. They had a mean free time of, what did I say here, 5 minutes or so. It gave a parity error and stopped, right? Well, the parity error was actually trappable, and I realized I could make it work. This is now me as opposed to Wilkes. On the next slide. What I did was simple. What I said was, what I would like to do is take the interrupt, go to a piece of supervisor code and clear the cache. Then it would automatically refill itself and clear the parity error. But you can't read the addresses in the slave store. You don't know which words are there, which is why we didn't do anything for a while. Then I realized all I had to do was cycle the entire memory, all 64K or 128K, cycle the entire memory, which will automatically refresh the cache when it finds a word which is in the cache, and at the same time correct the parity error. It takes a little while to do that, but you save a lot. I mean, if it didn't save a lot, we wouldn't have done it. I have to mention the file store. This was done by Sandy Fraser in 1966, and it was amazingly sophisticated. This I already mentioned is the structure of the store. He designed a file system on top of that, which looks very much like modern file systems, and in some ways is actually more advanced. So first of all, you've got a 3-part name, the owner, and 2 parts which are at the owner's control. So for example, I could have a file called DL201, which was what I was called in those days, /CCS/talk. There were control characters as the 4th part of the name. The letters A, B, C, D gave access controls. The A was the owner's access and D was everybody else. And B and C were people in some intermediate category, doesn't matter. So you can control who can read these files or write them. So in this example, the first 2 categories can read and write, and the rest can't. And the last character was the type of file. 3 letters, PTA. P is permanent, which means leave it on the disk and copy it to the tape archive. T is temporary, goes. A is archive only. So at the end of the job or the process, the disk copy is deleted, but copied first to archive. Remembering that in the end, we have a lot of users, and it's not a very big file store. We have strict quota control. Users need to be chary of overfilling their space. And it was a multi-generation archive. If you wrote something to archive and you already had something in the archive, it will keep both. It will keep 10 copies. And you can identify your file by 10 copies. You could go back to a generation ago or 2 generations ago. And that's a system that I don't think anybody has today. And yes, well, hardware. Hardware doesn't always work. Well, that's a surprise. So what happened when the disk broke? Well, trivially, a user could screw up wreck his file system and say, I destroyed my file system, please get it back for me. Or he could suffer a hardware fault that killed his directory. But we could have the ultimate test, which is the whole system dies. One of these large boxes dies. And we have to be sure that we could recover from that. There's only one way to be sure you can recover from that, and that's to try it out. So we did. We took a Sunday, and we declared the file system unusable and told the system to recover, and it did. You know, we were nervous to start with, obviously, and then when we saw tapes being asked for and chugging along and data being read, we were reasonably happy that it was going to work. There was a paper published. One of the things I've got there is a paper that was published in 1967 about file handling. Okay, so that's all the mechanics. What did a session look like? Well, the first thing is you didn't have to do anything to say, I want to log on. You just typed at the teletype, and the system knew you typed at the teletype. It knew this was a line that wasn't in use. It would tell you, wait. Yeah, you always had to wait because you have to look for one of these connections to the computer. And then the computer would type to you, user, i.e., what's your user ID? You type ID and the project, or if you just don't type the project and type return, it will type project, ? Basically. When we eventually implemented passwords, about which more in a moment, you would then have to put in your password, and there are other options you could put in. And it would tell you when your password was last used, and at the end of what you're doing, all you typed was finish. No magic words. In 1979, I went to a workshop designing command languages that were full of academics and 1 or 2 people like me who are practical people. And they said, the academics said, the way to log in at a computer has to be to type the word login bracket bracket. And the way to finish is log out bracket bracket. Why bracket bracket? Because they're functions, of course. We just thought that was totally stupid. Another interesting comment. In the very early days, we didn't have passwords. And Wilkes wanted to use the system, so he told him all he needed to do was type in his initials, followed by return. So he typed in MVWRETURN, and nothing happened. You learn about how to write manuals that way. We didn't have passwords to start with. We knew we'd have to have passwords. We implemented the password system. The staff didn't want it. I don't understand why. To this day, I don't understand why. They tried to subvert it by using stupid passwords like all spaces or 111111. A comment on passwords, we're using teletypes. There's no way to turn off the printing on teletypes. So you type your password in clear. So to avoid that, we pre-typed a set of blodges. That is 8 characters of 8 times something, backspace, 8 times something else, backspace, 8 times something else, until it was a mess. And then you type your password on top of that. So you couldn't read it. a little bit about how you did jobs or sessions online, input and output, numbered streams, not named like modern systems. So input 0 was terminal, output 0 was terminal. Any other number is at your choice. You had to know it and your program had to know it. For semi-interactive use, we designed something which was called a here stream. So you could say, like we've got in this slide, input stream 2 is here, and it's terminated by the character Z. The next lines contain the data, and the last line contains the Z. So that way you can construct a completely self-contained piece of code, which could then run non-interactively. All right, so normal mode. What was available in normal mode? I've got 3 slides, I think. These are general things. Obviously, a user can call a command, that is, create a command stream and say, obey that command stream. He can open a file, he can edit a file. The X means it was done, always done interactively. E3 was a line editor. Figaro was a calculator and an algebra system, written by 2 users, of course. Finish and help, very good help system, necessary. Type to type a file which you want to see what's in it, or you've just typed it, you want to check it. Send it to the printer, send it to the printer with line numbers, send a message, I'll talk about that in a moment. Type in a document ending by @q. Q for quit, I suppose. Type, do a password command, you can change your password, that would be how. Patch, binary changes to a program. Yes, confession time, we made a lot of use of that because compiling things was slow and laborious. And if you found a simple mistake, the easy thing to do is to patch it. We all know that, don't we? Time, obvious. Run job, signal, I'll send the message to Dick. I go signal, it comes straight to him. Closing a file, copying a file, deleting a file, looking at the files you've got to examine, filing away something, and choosing between the file versions. And these are the compilers which you've got available, quite a lot. Autocode, which was David Hartley's thesis on EDSAC 2, and there was a version on Titan. Et al, which is a symbolic assembler, IIT I mentioned. Fortran, Lisp, anybody remember Lisp? Yeah. MLS, which was a mixed language system, I don't know any more about it than that. BCPL, which was widely used from 1969 onwards, and others. Okay, so what did the session look like? I'm afraid I can't demonstrate it to you live. You have to come back in time to 1973. What I've done here is I've highlighted the things that the user typed. And this was the session that David Hartley did. He was a demonstrator at Data Fair. So I'm lucky. David had preserved this and sent it to me. So as a demonstration, David is wanting to log in. He types return, he gets this **** wait. Then user types in TFH200, which was his ID. The blodge, which is where the password went. Data Fair demonstrations, blah, 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 is a message of the day. You always got a message of the day between your password and anything else that happened. So just telling the world, like people trying to log in Cambridge, that we're currently doing demonstrations elsewhere. Maybe give us this break and let the system be quiet. Okay, so then he typed go, i.e., I've got nothing else I need to type, and the system said wait, because you never know, it could be a long wait at that point. Then tells him when it started, and he says input and types in a piece of data which has got mistakes in it. So he files it away, comes back to edit it interactively, context editor, he moves to line 1, he exchanges the EI for an IE, you can see what's going on. Puts in the comma, puts a space in, changes the word text, the word stuff, quits, and then he types it again. That was just an example of what you could do with the typing and editing. That's why it was in his data-fed demonstration. He then types in another document, which is a job. He has already written a program to evaluate primes. He's running a job to evaluate primes. And when it finishes, it will signal him. He's filed that as /JD. He then runs run job, which by default takes the current document. And then he does something else, waiting for that to finish. Types in a list of numbers. And notice the smallest number is -7999, and the largest is 10,000 and something. He files that away. He then gets the message to say that the job has run. He types the results file, and they are. Those are primes, I assure you, gentlemen and ladies. Those are primes. Then he runs the program, a program he had already written called maxList. He wants to find the largest number in the list of numbers, and he runs it, and the answer he gets is 79999, which was the smallest, not the largest. So there's obviously a bug in the program. So he types out the program. The bug is on the line which says arrow 2. It should say x greater than y. So he edits that and runs it again. I haven't put that in. That's the editing. And it's not all the files that he had, because you can see the last thing he typed was quit, i.e. leave examine. But in between, the second thing he tried to do was delete a temporary file. And it told him filing fault 200. So note that. Then the others he's deleted or left. Then he says, what did that filing fault 200 mean? So he says, I'm going to use help. Help with nothing else tells you how to use help. Help filing fault 200 tells me what the problem was. It was already open or being dumped. It was in use by the system. F-space tells him, the user, how much space of his quota he's used up. And that command said who else was online at the time. Room B and Titan were in Cambridge, and DataFair was in Southampton. So this was definitely a remote system. We could even play games. It's a game called Moo, which I don't know if people know. It's a bit like Wordle. So Wordle's got letters and Moo had numbers. So I decide on a number, 1, 2, 3, 4, and you have to guess it. And I'll tell you that you've got one number right in the right place and one number right in the wrong place, and the rest is you don't know. So then you repeat your guess. Moo was just a game interactively on Titan and a league table, and you could even write a program to be a player of that program. And there's a paper on the desk there from 1971 describing that, which actually I read in preparation for this talk, and it told me that my program was top of the league for a long time. That's the program, their paper. Okay, another very important thing we had was a message system. It's very important. As far as I know, we invented it. And there's a message at the end of this which resonates with today. So in 1966, there were no networks. There was no internet, no local net. ARPANET was founded in 1969, so 3 years later. The Janet network was 1984, so a lot later, although there were local networks between times. And there was no international agreement about protocols. In 1980s sometime, I was visiting friends in America, and they had a computer, and I tried to connect to our system in Cambridge. I could get as far as connecting, but they didn't understand anything I was typing because the protocols are different. So there's no I had no idea then that you could communicate that way with users of other computers. So our system was only to connect with people using our computer, local message system. So you type a command, you type message, and you send it to, address it to be to a particular user by his ID. He, if he is there, sees message for you, as we saw in the example. If he's not logged on, he will see that when he next logs on. The messages are stored in a file per user. It's rationed. Everything had to be rationed because disk space is scarce. And of course, we know it was amazingly useful. We know such a system is useful because we use it all the time. It did lead to a development which, if we had thought about it, was a harbinger for the future. A very clever user, I won't name him, I do know his name, requested a project for a thing he called GROGS, which I think means General Reverse Order Gossip System. His idea was that you have different topics and people can comment on them. It should ring bells, shouldn't it? It's just like the social media. But we didn't think of it that way, of course. And it was Cambridge only. What we hadn't anticipated was that it could become ugly. People, we know it now, people when they don't see each other face to face, don't have the same inhibition on what they write. And there are pylons. Polite people could become very nasty, which would have been a lesson for the future, but we didn't think about it. We didn't publicize it. And it only really occurred to me coming back to this talk. 1973, Titan ended. And I ran the last session. And this is a transcript, which I won't take too long with. Log in, same as usual. A long message today telling users, don't bother. Not much is working, and if you can use what there is, good luck to you. You can see it's 7th October 19. You can't see 73 there. And so what I did, this was a script which we agreed. I looked to see which systems these are the systems on disk which the operators can call on if they have a problem with the current running system. And it's only 2 copies of 2 systems because everything was very static in those days. And I wrote a job to copy the current system to tape. Ran that job, ended, and typed but not to the system, my comment at the end there. 7th October 1973. But something I only found out in preparation for this talk. I told somebody what I was doing. He said, oh, didn't you know that? Didn't I know that? If you can read it. The event had all been well rehearsed, with at least 2 minor sabotaging efforts added to the fun. Fun was not my fun, it was their fun. Barry Landy was at the master console in the Titan room, and the camera cut to him as he was about to shut the system down. Someone, overnight, no names there, had tweaked the code so that the Titan refused to die quietly, and Barry had to use all his deep understanding of the system to bypass this challenge. I remember none of that. The film shows him frantically typing at the console and eventually shutting the system down cleanly. Phew, as I say, I really don't remember that. They had also sabotaged the master off switch. So the next thing I did was push the master off switch and nothing happened. But that wasn't my job to fix. Okay, what happened next? Oh no, how many users did we have? I have no idea, really. I've not been able to find out. I found nothing in writing. I've asked various people. My guess is in the thousands, maybe up to 2,000 different users of our system with various priorities and so on. Could be more, I don't know. Oh yes, what went wrong? Lessons from that system. Hardware unreliability, software unreliability. Users must back up data frequently. No longer quite so necessary, but they don't do it. And I've had to rescue people who've lost months of data. We thought our system was secure. We allow people to read the software, the operating system. The password file could be read in its scrambled form. Well, people could unscramble the passwords. And we didn't think that they'll be able to unscramble the passwords, but they could. There were unexpected ways into the software, so that's the usual people, malicious hackers. Password guessing, wife's name, 1, 2, 3, 4, 5, 6, 7, 8. And an important lesson which we didn't learn at the time, uncleared memory and disk space. You get a program, you get given a chunk of memory, we didn't clear it, so what was there beforehand was still there. And if you were an assiduous user, you could do this repeatedly and glean information. Same is true with disk space. You ask for a file of 200 blocks, well, it's not cleared. Okay, so briefly what happened next. The Grants Council allowed us to buy an IBM 370-165. Why? Because, first of all the other things they offered us were no more powerful than Titan, which seemed a bit stupid. 370 was more powerful, about a factor of 4, I think, and it had a time-sharing system, TSO, the new IBM time-sharing system option. And we were definitely not going to write our own system. Not. And they showed us a simulation of 30-odd users who got sub-second response time. But this was a killer, absolute killer. We were still using the teletypes. IBM control of teletypes, when the user stopped using it, it went ram, 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 ram. They rattled the keyboard. Why? Because otherwise you might think the system had died. But you can't think. You're waiting for your job to run and you can't think. So that was possibly the worst thing. The response, this is bad, was multi-second, not sub-second. I dare say if we'd run their script exactly like they'd done in the simulation, it would have been sub-second. That life's not like that. No integration in the background and foreground. People hated JCL, they still do. So what did we do? We developed an online interface. We didn't write a totally new operating system, no. We did write a new command system, which people could use, which used the given interfaces that TSO used. We integrated the online system with jobs by run job command, just like we'd done for Titan. And people are happy with that. We called it Phoenix because it rose from the ashes of Titan. PHX for short. Closed in 1995. And in 1972, that's during the intervening period between Titan still running and the Phoenix system starting, we got this letter from two people who were algebraists. They're the people who wrote that Figaro program, just saying how much they appreciate the Phoenix system and they can do so much more online than in jobs. Well, we all know that. Thank you very much. So just apart from questions, I've got stuff there that people might like to look at. Please don't take anything away.
If we can move this.
Sure.
Some of us couldn't actually see much of the screen.
Oh, sorry about that.
Well, pull it out.
Sorry about that.
Well, you'll,
Not my fault. No.
Unshare that, Darwin, while you.
Not the room ones.
On.
So it's very difficult to get anything else.
No, it's above you now.
Well, thanks, Preston.
Bobby, would you like to unmute yourself?
No. I'm unmuted. Yes, can you hear me?
Yes, we can.
Okay, right. Yes. One quick thing before I start. When there was talk about the board from the Atlas earlier on, I reached out my right hand, and I think that looks remarkably similar. I have a cache of these things. It was literally at my right hand, and I hadn't prepared in advance. What I really wanted to say was, thank you very much. That was extremely illuminating. Particularly illuminating, I think, because I can see in it the germs of some of the things that I encountered later on. I was involved for nearly all of its life with the Kent Online system. And that was, of course, originated by Peter Brown and Heather Brown and a few others who'd been at Cambridge. And I can see now where some of the ideas came from and where they went. I mean, they put COS up in 1969, I think. I arrived a year later, and I spent the next 5 years hacking it badly. And getting very, very unpopular with some people until I ended up being the actual manager. And then, of course, it's the usual thing, you know. So, always make the best poachers always make the best gamekeepers. So thank you very much. I mean, it has illuminated a lot of the little sort of background holes. It's very good.
Thank you. Thank you.
Might I try and shed some light on the mystery of what was the name of Beeline? It goes back to Manchester Mark I machine. Remember, the early Manchester machines had their store on cathode ray tubes. And one of the cathode ray tubes held the accumulator that was in a line of dots, or not dots, that was called the A line. And then there was a second one, control register, and then in between, at this point, they introduced the idea of a modifier register. So that became the B line.
Thank you. Thank you.
Yeah, John Davis. You mentioned David Barron. That's a name that rang bells with me. Was that the David Barron who founded Computer Technology Limited, CTL?
Yeah.
Yeah, it's Ian Barron.
For correction.
More questions. Let me ask one if I may. You talked about TSS on the 67.
TSO.
Referring to TSS. Question goes away. That was 65.
I suggest you walk a few feet further so the ceiling microphone.
I was just going to tell you a little anecdote. Firstly, David Barron, I remember him. He produced a wonderful paper in Computer Journal, a short note about the come from statement, which was a kind of follow on to Dijkstra's famous go-to statement, considered harmful. I also remember a conversation with Peter Hall from ICL, who chaired the Manchester CCS group. And he said how the machinations that went on to get an atlas into Cambridge involved some very creative accounting.
Hello.
Waving in hand.
Hello, it's Jim Brooks. Can you see me? Hear me? No?
Jim.
Hello?
Yes, we can hear you.
You can hear me okay? Yes?
Yes.
Barry is standing in front of the speaker.
You're muted, Jim.
Mute yourself.
You're muted.
Jim, you're muted.
Is he?
Yes.
Yeah, it's this wretched technology we've invented, isn't it? It's different on every single system I've got. So excuse me for that. But no, I just want to say thank you very much. That's a really entertaining, illuminating presentation on a machine that I was in a way quite close to, in a way never saw, and that's the Titan. Because I was working for Ferranti in Manchester in 1962, and the Atlas, the Titan, I only knew of through conversations with David Barron, who's there somewhere. David, hello. And David Hartley and David Barron over a pint or two at the old college inn just around the corner from the Manchester electrical department. But the point that I was just about to try and bring out was that in '63, Ferranti, through Chris Wilson and Basil Ferranti, set up a team to go to the United States to try and sell this massive machine that we'd seen built over there, here in Manchester. And I did go to MIT and met the Project Mac team as part of my sales round. And I gave a presentation of about an hour to them about the Atlas system. And that dragged on into about 3 hours. And it had all sorts of individuals, the Project Mac director, and Farno and Cabato. And these are the guys that Maurice Wilkes would have met about 2 years later with the CTSS system, which, if I remember, was on a PDP-6 running 6 terminals at the time. And they wanted to scale up and they thought Atlas might help. In actual fact, we then worked. I got Frank Sumner assigned to me from Manchester University, and we specified the replacement for the PDP machine so that it looked rather like the Atlas. But we had to go out to tender, and that was fine. And there were no real competitors for Atlas, so we were about to be placed an order, and the American government said no, it had to be. It was such a big order and such a big system, it had to be homegrown. So we helped, if you like, specify the machine that eventually became the Honeywell Multex. And so it diverged a little from the Atlas and Titan, but it was a very successful machine in its way. Anyway, thank you. I just wanted to say thank you, very, very interesting.
Thank you.
So, David Hartley is online. Did you want to speak, David?
Am I online? Yes, I am, aren't I? Yeah. Could I add to Barry's talk? And he doesn't know this. I'm going to say it, but I couldn't resist the crack. He mentioned the problem we had later in the life of Titan of users being naughty, and it was a serious problem. And it got on worse, actually. It got on worse on even the bigger machines later. So much so, the university has the rules which says you shall not do this, you shall not do that, and they could be fined, they could be tried, and all that. I was director at the time, and I had to be the judge and the jury, and I even fined somebody £500, and that's how serious it all was, and it wasn't quite fun really, but it's worth recording in. Can I say, Barry, thank you very much for the comments and all that, and thank you very much for reminding me what a wonderful team we were. Thank you.
Thank you, Dave.
Brian Knight. You mentioned on Titan you had to solve various problems to run multiple user processes at the same time. I was wondering whether you found yourself solving much the same problems on the IBM 370, because it also didn't have virtual memory, and when you swap things out, you had to swap them back to the same physical address and all those things. You erased it from a lot more memory, but it only had a few protection regions, didn't it? So you couldn't run hundreds of programs in parallel. You couldn't run hundreds of them, though. You could only run a few and protect them from each other.
It has storage protection keys.
16. Okay.
I think he introduced core granules to do core swapping rather than swapping to disk.
Yeah.
I think that was one of the additions to Phoenix.
I remember something about it at the time, but it wasn't.
Yeah, just to say that the problem of IBM over-promising into the real world at my end, where we had an IBM salesman who gave a refresh rate for the screen. And he was really talking about, just refreshing the data that was on there. Of course, our customers assumed that it would be the refresh rate with the modified data. And we had to pull all sorts of tricks, including data modified flags and everything else, to make sure that we could get the data up and back down a 2400 baud line and keep the customer quiet, which is difficult.
We can't see everybody online, so bear with us.
Is that we can't hear what you're saying over here. We'll try and get that. Stop.
Somewhere else. Well, I've gone back to your microphone that you're wearing, and I'm not saying.
Unmute it. It is muted at the moment if you press that button. Yeah, that's like.
Okay. Any more questions? Yes, gentleman in the back.
As someone who grew up on Phoenix, how much of the Titan and IBM software still exists?
In what form?
Titan software even.
Or printed.
I guess the background to the question is, what's the potential for using a simulator to run some of this?
Yeah, it's definitely on paper, which isn't the answer you wanted. I had believed I had a copy on disk, my disk. When I last looked, it didn't seem to be intact.
Did I hear you say you've actually got paper printout of this? Can we communicate later about the possibility that
There's a lot of it.
Yeah, but
yeah, sure.
I've been involved with rebuilt
David,
Leo 3 systems from paper printout, which weren't in such good condition.
You know how to contact me, sir.
Yes, yes.
Oh.
So you mentioned messaging and then indicated Twitter and the like, but your messaging sounds, with the different topics, sounds like KICS, or the Computer Information Exchange, which is the British version of CompuServe, which people will have heard of.
Oh, sorry, it's
Some of the topics, it sounds like a sort of in between. KICS is.
well, it was open to any user of the system to comment on anything. So in that respect, it's like the general systems we see today, Twitter and the like. Of course, number of users is measured in hundreds or thousands and not millions.
Yeah. But you talked about being in different topics.
Yeah. It was sorted by different, it was basically just the message system. Instead of users' names being the key to a string, it was the topic name.
Pick up on this future. The Atlas 2 from Cambridge, I think, went to the CAD centre in what is
No,
that?
that was another machine.
Sorry?
That was a second machine.
Right, but it didn't run your software.
It did. It did run us. Yeah, I put it there.
Sorry.
And this was part of the deal. When they got that machine, part of the deal was that I would modify it, modify our system to adapt to their different hardware, because they had paging, we didn't. And they would run our system, which they did. And at that particular time, our hardware was being relocated. A matter of some 50 yards or so, but it's not trivial game. And while our hardware was being relocated and re-verified, we used their system. So people logged in and they didn't even realize they're on a different machine.
Fantastic.
So you see where my suspicion of the movement of the machine came from.
Yeah.
Excellent. We seem to have had all our questions answered. Mary, that was magnificent. And it was funny, and it was illuminating, and it was educational. Thank you very much indeed.
Well done.
Thank you very much.
Ladies and gentlemen, our next meeting is our traditional film show, which will be on December the 11th. And for those who are creatures of habit, please note that is the second Thursday in the month, not the third. So we look forward to seeing you then, and there will be more in the new year. Thank you all for coming. That was great. Okay. It was a pity you didn't have a 67. There was others.
161.
There was one, yeah, it was later. Yeah, I worked on the 67. And TSS, which was the operating system for that, was a complete disaster.
Yeah.
We worked with CBCMS.
165 is not really stopped. You've got the 38 and 4.
Okay. It went on and up.